So
I recall the flu we had in 1957, 58. And although it didn't get the attention that we're getting now, it was about half as many people died as per capita as now, but many more people got it, particularly students. It said about 75% of all the people over in the US over a 6-month period got the flu. I recall I was in college and you would have half or 3/4 of the students would all be sneezing and coughing but we went through it. But it was interesting how bad it was. But I think the country was much more resilient in those days.
oh, they were tough in those days. None of this mamby-pamby stuff we've got now.
Well, you know, maybe on the,
Eisenhower was president and had come back from World War II, and a little flu wasn't going to bother the country. He didn't think.
well, maybe on those culturally sensitive notes, I'll introduce our speaker today, and we're really happy to have one of the pillars of the geotechnical, geoscience, and geomechanics community with us today, and that's Professor Derek Elsworth. And Derek is professor in the departments of engineering and mineral engineering and geosciences, and he's affiliated with the Center for Geomechanics, Geofluids, and Geohazards, and this is at Penn State University. As most of us know, his interests are in areas of experimental and computational mechanics, rock mechanics, and mechanical transport in fractured rocks, sequestration of radioactive waste, CO2, just about any sort of cutting edge technology that one can think of. And Derek provided us a very brief and modest abstract. We could go on for quite a bit, but I think I'll just turn it right over to Derek to get to it.
Fantastic, John. Thank you very much. Can everyone hear me, by the way? This is my new thing. So you said 45 minutes, but I'll do 40 and I'll try and work to that. 40 minutes for me to talk, right, gang? And John?
Correct.
Yeah, okay. I just looked at that. Well, great to be online. As we were saying before, interesting what Zoom allows us to do these days. I have to admit that I'm a little zoomed out myself, so I appreciate you joining us today. And we're going to talk a little bit about some of the work we've been doing maybe over the last decade on gas fracturing. And most of the work that's we'll talk about today is done by two authors, Quang Gan, who's now was at Aberdeen and is now in Chongqing, and primarily Jihao Wang, if I get my system working again, who is now at Chevron. And so we forget what life was like before March of 2020, but we used to gather together, I remember. And so this is part of our group, I don't know, from a few years ago now. But Jihao is the second from the left and the back and is now at Chevron. And so the main questions that I'll attempt to address anyway is what are the best forms of fractures to have? And so you can look heuristically that penetrative fractures that are long and have lots of proppant in them presumably are the most useful. Perhaps they're not the most environmentally successful, but can we quantify exactly what the characteristics would be of a fracture that would make it the best? Is it the longest, tallest, or widest, the highest proppant charged, the most complex in terms of branching, the best matched to the fluids already in the reservoir with the fracturing fluids? Or is it indeed, in addition to the kind of production aspects, is it the one that has the lowest environmental effects? And so to kind of address those in a roundabout way, we'll look at using gases, which perhaps is a bit esoteric for hydraulic fracturing, certainly not probably cost effective. But let's see what the characteristics of gas fractures might be in a variety of different forms. And we'll look at two different forms: static gas fracturing, where you lose the gas like a regular slick water fracture, and dynamic gas fracturing, where the pressurization rise time is much faster. Not as fast as explosive fracturing, but much faster than in conventional hydraulic fracturing. And we'll look at the issues that are related to that. And of course, we all know that the last 15 years, the shale gas revolution has been brought on by two features: horizontal drilling, to be able to put out laterals over long distances, and of course massive hydraulic fracturing to be able to reach into the reservoir, alter permeability, reduce diffusion lengths, and therefore recover fluids effectively for essentially nano Darcy permeability rocks. And so the motivation for gas fracturing motivations are many. Energetic fracturing potentially is more penetrative by perhaps making a dendritic network that has shorter diffusion lengths. So on the production side, you perhaps can imagine that it might be beneficial. But there are also incidental benefits. Reducing water usage, where water is a valuable resource, you could imagine is useful. You don't have to re-inject the fluids from flowback, potentially. So you perhaps reduce environmental effects. And if you're using a gas rather than a liquid water, you reduce norms coming to the surface and the potential for occlusion of pore zones. And so waterless fracturing isn't new. It's been around. Oil-based fracturing fluids have been used. Explosive fracturing has been used. In fact, I think that was the original stimulation for Drake-type wells in the days of Pennsylvania as a producer. And of course, gas fracturing has also been used using LPG and nitrogen and experimental approaches using CO2. And most of these have tried to take advantage of the idea that you can perhaps make more complex fracture networks, perhaps not. But the negative is that you can't necessarily carry proppant with them into the formation. Why am I? Okay. So we'll look first at static fracturing using gases. And here are some little toy demonstrations. In this case, looking at the bottom figure along a borehole. So you see the top figure, a borehole. If you imagine looking from your left side into that plexiglass block, you see the coupling, a small borehole that is pressurized, in this case with water. And ultimately, when it reaches the breakdown pressure of that unstressed block, stressed in this particular case, it breaks down. And so you can do these experiments with water or other fluids. And here are some results on the left-hand side from doing these toy demonstrations, unstressed, but with water, oil, CO2, nitrogen, and helium. Rock on the right-hand side. And the kind of really interesting feature of this is that the breakdown pressures for these identical experiments, but with different fluids, are different for CO2 and nitrogen by a factor of about 2. And this originally was kind of a mystery to us as to why this would be, as to why different fluids would have different breakdown pressures. The other thing that occurs at the same time is that the different fluids, different gases that are used, have different levels of complexity and repeatable complexity in the features that they make when they fracture. And not quite certain that the two are related, but the two actually occur. And if you plot the degree of complexity, and complexity here is not something fancy like a fractal dimension. Well, of course it's not if it's 5. But it's just the number of wings that you have on a fracture. So 2 would be a bi-wing fracture, 3, etc., triple wing fracture. And if you plot breakdown pressure with the complexity, you end up with these 2 groupings for gases which are subcritical at the testing temperature in the lab, and those that are supercritical. So CO2, of course, jumps this boundary at 30 degrees centigrade from subcritical to supercritical. And so this was kind of a conundrum to us. And so the person who worked this out, along with me, of course, was Tran Gan, who was at Aberdeen and who recently just moved to Chongqing University. And the hypothesis was that if you're generating a pressure within a borehole, and if you seal that borehole against the fluid penetrating into the wall, you get the Hubbard-Willis breakdown pressure, which if it's unstressed, is roughly half the tensile strength. And if you pressurize the borehole but allow leakage into the wall, it roughly cuts that breakdown pressure by a factor of 2. And so it's this penetration into the well that occurs in these plexiglass specimens, analogs for shales, with floors in them. And if the fluid cannot get into the floor, then the breakdown pressure is double that of what it would be if it's able to penetrate into the wall. And so it's all controlled by capillary pressures, excluding the fluid from doing that. And this works for supercritical fluids rather than subcritical fluids, because supercritical fluids in conjunction with each other, two supercritical fluids, are immiscible. They are not immiscible, and therefore they'd have no interfacial restriction on invading the wall. And you can show that quite easily by plotting the data for all these breakdown pressures here, shown as a function of the temperature relative to the transition from subcritical to supercritical pressure, temperature rather. So everything on the right is supercritical, everything on the left is subcritical. If you plot the breakdown pressures on their own, the breakdown pressures are roughly half of the tensile strength of the plexiglass, about 70 megapascals, so 35 of that order. And if you plot these same data, but merely by dividing them through by the interfacial tension of the particular fluid, then all of a sudden these data on the right-hand side become disordered, and the subcritical data become absolutely ordered, suggesting that this is a reasonable, it's got to overcome the entry pressure. The permeabilities of all the rocks are the same, so the floor dimensions or apertures are probably the same. And so it should scale with 1 over the interfacial tension of the fluid. And so that suggests that that's the reason for breakdown. It doesn't say anything necessarily about the complexity, but it says something about the breakdown. The other reason in looking at gases, so this is kind of out of step, but is to look at the effects of dynamic gas fracturing. And so rather than just raising the pressure slowly to be able to fracture it like a normal hydraulic fracture, you apply a relatively rapid pulse of gas in the system. And this has been, and we'll talk about a particular tool that has been used quite successfully in China. Now this was taken, I think, 7 years ago, in a very hot July day in Huinan, where they have an extensive network of horizontal drainage holes draining gas from coal seams before physically mining it. And so our discussion here is not so much about hydraulic fracturing, not about explosive fracturing, but what we'll talk about is dynamic fracturing. And both hydraulic fracturing and explosive fracturing have been used before. And I won't say any more about those. But the essence of what we'll talk about in terms of dynamic fracturing is really just the rise time for the pressurization pulse. And so if you look at the length of time that you pressurize, then dynamic fracturing is something intermediate between very high explosive gas pressures and relatively low but highly sustained long duration fluid pressures. And this can be applied by what's referred to as a Carnot experiment. So carbon dioxide overpressures. And it works on the principle that you have a closed chamber. It's a tool that goes at the end of a line into a borehole. It has a rupture disc applied to a cavity. That cavity is filled with CO2. The cavity has a heater in it. And once it's put in place, the heater heats up the CO2 to raise the pressure. As the pressure gets too large for the rupture disc, it breaks it and it gets pushed out into the formation, jetted into the sides of the holes and causing these penetrative distribution of fractures, which come out of these jetted locations, but also rather radial in format around the hole. And of course, we know that hydraulic fractures follow the direction of the maximum principal stress, perpendicular to the minimum principal stress. If you want them to be radial, you have to be able to engineer it so that the in situ stresses are roughly equivalent, and then you can do that. But of course, in explosive blasting, the inertial effects of the loading on the wall is really what gives you this all-around stress, which completely swamps, overcomes the in situ stresses, and potentially gives you the ability to be able to develop this radially penetrative network of fractures. So you just need to be able to include the weight in the inertial effects in the wave equation for looking at the stress effects. These are some data from Wancheng Zhu from Northeastern University looking at damage mechanics models stepping in time from left to right, looking at the different stress regimes as you apply a pulse on the borehole wall that propagates through the system, and as a result of damage generates permeability, and that permeability takes on this form which tends to be not an infinite number of radial fractures, but a limited number. In this case, something 3, 4, 5, and repeatably, it's a limited number of fractures. And so our interest was in understanding exactly the mechanisms behind that. The controls are quite clear. Kind of it's shown in these models, not of blocks which are unstressed, but of in situ stressed boreholes, where the regional stresses might be uniform. You get radial fractures developing. Where they're large, these fractures are suppressed. And where they're oblique, then you tend to get the fractures following the in situ stresses. So you have to have a big enough stress to be able to completely overpower them. So we, at least in principle, understand the mechanisms by how that works. The one question is, why do we get 5 fractures or 3 fractures or 4 fractures? It'd be great if we got 100 in some respects. Is it possible to do that? Or are the controls that stop us from being able to do that? And so what we'll do is kind of examine the conditions by which we generate this dynamic overpressure, the dynamic gas wave giving a dynamic wave in the solid of the rock, and then what happens with the gas pressure after that. And so one way to look at this is to be able to understand exactly the magnitudes of the stresses that are developed as a pressure wave is applied to the borehole wall. And so that's what's shown here. These are the individual overstresses in tension that are shown at different times for different rise times of 20 microseconds and 200 microseconds. And the locus of these tensile stresses as you go into the borehole wall tells you the maximum tensile stress that the wall experiences. So if you compare that, for instance, to the tensile strength of the rock, you get out of it the fact that this dynamic wave gives you something like 6 radii of penetration that a fracture could propagate into and exceed the tensile strength. And if it's stronger rock relative to the overpressure, then it doesn't go quite so far, maybe only a couple of times. But you can rationalize exactly the penetration of this initial starter fractures as they go into the wall. And you'd expect these to have azimuths that go around the whole 360 degrees of the borehole wall. It turns out that these overpressures, even in the dynamic state, are pretty close to the 1 over the square drop off in terms of stresses as you go away from the borehole wall. At very slow, fast rise times, the exponent is 1.5, but for 2 milliseconds, it's already the fall off in the stress is according to the square of distance, square radius. But then the second mechanism from these starter cracks is those fractures being filled with gas and generating hydraulic fractures, gas fractures that emanate from those. And so the question is, how do you evaluate whether you get 100 fractures going out or just 5 or 6? And so one way to do this is to choose a geometry where you have unequal fracture lengths, a long one and a short one, and look at them for wellbore loading, gas loading along the fractures, and gas loading fully along the fractures, and see if you can understand exactly what the tendency is for that behavior. And to cut a long story short, is you can look at the stress intensity factors, how they vary along fractures for a variety of different lengths, where you look at the ratio of the length of the 2 different fractures. So for bi-wing fracture, where you have equal lengths both left and right, the obliquity ratio is 1. If this is a very big fracture relative to the left-hand fracture, the obliquity is a big number. So this is just the obliquity of the 2 fractures. The red dotted line is the stress intensity factor on the short fracture, and the blue line is on the long fracture. And so if you have a stress intensity factor on the short fracture, which is larger than the in situ strength, the fracture toughness of the material, then it will tend to extend the longer fracture. The obliquity will go down, and it will tend towards equal bi-wing length fractures. So when this red dotted line is above the blue line, you get a tendency for them to become equal length. When the opposite is the true, when the long fracture has a higher stress intensity than the short fracture, you tend to get the longer fracture propagated, and therefore you'll end up with long fractures, and the short fractures will go nowhere. And so you can do this for loading at the borehole wall, which is what these are for. And you see basically that for a small number of fractures, they tend to reach the same length. For a larger number of fractures, you get every second fracture being long and every intermediate fracture being short. If you do that then for, I don't know why it's not moving, for fractures that are gas filled along their length, you see again, for a small number of fractures, you get the long fracture, the short fractures extending preferentially, and for a larger number of fractures, you get only a limited number of the long fractures extending and the short fractures stay static. So that, in some respect, explains that you're limited in some way to being able to generate the number of fractures to maybe 3, 4, certainly we see it 5 in numerical simulations. And it seems to be rationalized in terms of this behavior. It's very similar, if any of you have seen the classic Nemeth-Nasser analysis of chilling a half space. You chill a half space, you develop tensile cracks in the half space. You can imagine them being an infinite number of these floors. They all propagate, but every second one shuts down as the next one next to it gets larger and its influence grows. Then those, every second one grow, every second one of those shuts down. And so you end up with like a fractal distribution from a surface. Slightly different, I guess, from a borehole wall because it's different geometry, but I think it's the same system. So static gas fracturing, dynamic gas fracturing is where the rise time is different. So now we'll turn back to static gas fracturing, and we said that we see 2 features. One is we get breakdown early. That's an interesting thing. I'm not sure that's of great relevance. It's an interesting behavior. But also scaled with that breakdown pressure is the fact that complexity changes in the system. And so we might be interested to use gas to develop, even for static gas fracturing, increased complexity. But the issue, if you do that, is that the gas doesn't necessarily carry the propants as effectively as a liquid. Some of these gases will be liquids, but less dense liquids and with low viscosities. And so the question is, how well do you expect them to be able to carry propants along the fracture? And so you can use very sophisticated models to do this. PKN is not one of them, but it's certainly a rational method to be able to look at the major features of driving fractures, idealized fractures, and it certainly allows you to compare apples with apples. And so for different gases, you can compare, it might not be a perfect solution, but at least you can compare different gases under the same relative conditions. So as many of you know, PKN works on an idealized fracture, conservation of mass within the fracture that obeys Poiseuille's law. The fracture has a set geometry, kind of Steddon crack geometry. It works on balance of a rheological fluid, and that rheological fluid is propant and viscous Newtonian fluid added together. And the propant fluxes are in 2 forms, an along fracture flux, which is carrying the propant downwind. There's some jamming mechanism that you might have to include, this one by Igor Dontsov in this particular case, where if you get 3 or 4 propant diameters of fracture across a fracture, then it doesn't go anywhere mechanically, irrespective of the fluid conditions, so-called screen out. And also you get settling of propant within the fractures. So it's like throwing a ball. You throw the ball further, gravity acts less on that because the ball's going fast. It acts the same, of course, but it will go further before it comes down to the ground. And so in that modality, you can do these experiments to be able to compare PKN fractures being driven by water and look at the evolution of fracture width as you go down the screen here in terms of different lengths of treatment, 2000 seconds being the bottom one. Of course, that's the only relevant. And you can look at the evolution of the beach that develops within this fracture. And you can do it for water, you can do it for LPG. You can see these scales are actually changing. We'll look at the ensemble at the end. You can do it for CO2. You can do it for ethane as a byproduct from shale gas, which is a glut potentially. And you can look at nitrogen, where you see not much of proppant formation at all. And you can look at them together. And so if you look at the beaches that develop for each of these, you see that the water fracture is longest because it has the less leak off than the lower viscosity gases. You can see the beach that it makes is longer, and you can see the relative proportions of these and the sizes of the fractures that develop. And so you can see that for gases, the ability to carry proppant down the fracture perhaps isn't so great. And so you can ask yourself, what are solutions to be able to increase that penetration? So one would be to use gels. And so you can use gelled LPG. And so all we're doing, all GHOW is doing, is changing the density and viscosity to be appropriate for that particular liquid. So you get equivalent rheology for that. And now you see that gels potentially for LPG don't do so much. Perhaps they carry it further downstream. You can gel CO2 to change the characteristics. And if you do that, actually you get, I think these are on different scales in terms of the proppant concentrations, and you see that has some potential to carry the proppant further downstream. You could use less dense proppants, expensive of course, but the idea being that going at a given velocity, if it's settling out slower, such as will be the case for a less dense proppant or a smaller diameter proppant, it'll carry further down the fracture before it settles out, and you can see some effects of looking at that. You can use foams potentially. It always seems backwards to me that the lowest quality foam is the least dense but the most effective as carrying things down gradient, which seems kind of strange, but it works out to be that way. And so you see the change in the diameter, the widths of these fractures, and also the proppant concentration that gets carried down most effectively by the lowest quality foams. And then you can try and rationalize these behaviors in terms of seeking how far these different lengths of penetration will be for different gases and different proppants by trying to just do a very simple dimensional analysis. The dimensional analysis is really how far can you throw a baseball. And the idea is that the proppant has a given horizontal velocity that's defined by the fluid which is transporting it. It has a settling time which is given by the rate at which it will fall within the column. And if you combine these two together as a velocity times a time taken for it to settle, then you can find out how far it will go. Nothing more than that. But what it does allow you to do is potentially codify the results that we've talked about now in terms of how far it will go for a given condition of different fluids and different proppants, and look at the parameters which control that behavior. It scales with, it goes further as viscosity increases because it's able to carry it more effectively. It scales inversely with density. So the smaller the density contrast, the further it will go because it's less negatively buoyant. And also it scales inversely with the diameter. So the smaller diameter particles will take longer to set up. But it gives you the scaling relationship in terms of the exact coefficients that you should look at to look at that scaling relationship. And it gives you an envelope for those behaviors. So that's the ability to be able to calculate exactly how far the proppant would go. So now a remaining question is, which one of those models is the better? Is it better that you have a small slither of proppant going a long distance, or a big fat wad of proppant going less far, but acting to be able to have a more conductive hydraulic fracture by virtue of the higher proppant loading? And so rather than just do that by heuristically or arm waving as to what it be. You can also look at trying to understand what happens once the proppant has been propagated and deflation occurs. And as deflation occurs, the proppant will close, flow back will occur, and flow into the formation will occur. And you can imagine getting from that a transition from a PKN type fracture into a fracture which has closed that lacks proppant, a fracture that has a loose concentration of proppant that will close and capture that loose proppant and be propped open by it. And the beach that sits at the bottom of it will be your high conductivity component. And of course, you might get some interesting areas between these where you perhaps don't have proppant, but you have interesting architectures of the fracture. And so that's exactly what Jiahao did. You know, applied some kind of Green's kernel function to looking at the closure of the fracture to be able to divide it into these areas that have just fracture walls, loose concentration of proppant, which compacts a lot, a beach of proppant, which doesn't compact very much, and then apply to that some magnitudes of permeability that are representative of those from Cozzini-Kármán type relations. And so this is just a simple illustration of what that would look like. Perhaps you have a fracture that stands vertically and looks like this. This is exaggerated in terms of millimeters versus meters. This is the beach for the initial proppant distribution. The fracture width will change over time from its initial form to being compressed, being kept open by the proppant here, but being allowed to close here. And the stresses will slowly redevelop themselves in the proppant as it closes. And from this, you can get, if you use some kind of estimation from Cozzini-Kármán of what the porous medium permeability would be, you can get conductance of the fracture as it closes. And that's what you're left with here. So that's essentially what we're doing in these forms. So you can look at these same kind of simulations, but instead of just looking at the proppant concentration, you can look at the widths of the proppant pack, the residual aperture that results in the fracture, the conductivity of the fractures that result with these kind of high conductivity zones that exist above the beach before you go into this low concentration proppant, which is interesting, and also a high concentration at the base of the fracture, I think by virtue of an open portion of the fracture. And you can look at the stresses that are driving that compaction in the system. So you can do it for low viscosity fluids and all the different behaviors that we looked at. And so these are for large proppant versus ultralight proppant. So for large proppant, it settles out quickly and has a high permeability zone right at the base, but it doesn't go as far as the low density proppant, which is much more equally distributed top and bottom of the median line of the fracture and has gone a long way because it hasn't settled out early. You can look at regular slick water fracturing with the proppant not going so far, actually going quite far. These are different length scales, 400 versus 200 in this particular case. And you can look at cases of screen out where fast leak off into the formation leaves proppant close to the tip stranded and then results in the essential blunting of the fracture and the termination of proppant, termination of fracturing beyond that. And so with that architecture and that known distribution of fracture conductivity, you can go and then apply models to be able to basically look at how effective that distribution of that reservoir, the ensemble behavioral reservoir, drainage from the rock itself that may be microdarcy permeability into the fracture and then along the fracture. And you can examine a number of cells that are representative of this kind of repeating geometry of a single fracture, a half width reservoir between this and the next fracture, and what the proppant distribution on this face means in terms of the conductivity it gives in delivering gas from the reservoir into the central well that goes down here. And if you do that, ignoring the features on the left, you have some distribution of potential cumulative production. Again, I'm not sure that the amounts matter, but the ordering perhaps says something about the system for running this over, I guess, just 3 years, 1,200 days, and for the different kinds of stimulations that we've done, from driving the fracture in the first place, carrying the proppant with that fracturing fluid, and then allowing that distribution of fracturing fluid to dissipate both into the formation, and I guess these were locked in. So I think only into the formation, and then to look at the potential gas recovery from those systems. And so you see this ranking, if you like, of different things in terms of using foams, gelled CO2, slick water being intermediate to these. Of course, these are much more expensive potentially than using slick water, and then less stellar performance for materials as we go down to comparing apples to apples, the same mass flow rates given for the same lengths of stimulation for LPG, CO2, ethane, and gas, nitrogen gas. So these are the true gas fractures on the bottom, static gas fractures. These are modified gases with foams and gels on the top, and also slick water. And so, well, for the cost of doing slick water, it would seem that none of these could be economically viable, but I think our aim in this has been to understand something about the mechanisms and to be able to just understand what the rankings of these different components are. So anyway, I've purposely gone through this quite quickly. I see I've been going for 35 minutes, and I don't plan to take much more than 40, which is my original idea. And so to summarize, we've talked about these 4 topics. So static gas fracturing, lower breakdown stresses, and changing in complexity for these toy examples between supercritical and subcritical fluids, which is kind of curious in itself. A mechanism to explain that. Dynamic gas fracturing, perhaps it doesn't have the hundreds of meter reach that hydraulic fractures do from well bores, but certainly has 10, 20 meter reach in coals, and could have similar reach, perhaps meters reach, 10 meters reach in shales if you have the right conditions. We don't know. Has an interesting characteristic in that these dynamic fractures have this dynamic loading which overcomes to some distance the radial stresses around the borehole, the stress regime, and perhaps allows you to get penetrative fractures that aren't limited to this bi-wing geometry, which potentially reduces diffusion lengths or drainage lengths between those fractures. So static gas fracturing, dynamic gas fracturing, and then back to static gas fracturing to be able to look at the behavior in terms of where the one important feature is perhaps being able to carry proppant down the fractures. And so I'll just go through the summary here rather than ad-libbing it. The advantages, of course, are that it potentially could allow you to not use water. And so there's certain environmental desires with that. Potentially, it could be more productive if you can work it into a way that's more penetrative. If greenhouse gas ever becomes a commodity that has a dollar amount attached to its disposal, then perhaps that changes the economics all of a sudden. And if enhanced shale gas recovery using pumping of CO2 into reservoirs or storage of hydrogen ever becomes an issue, then these issues of fracturing with gases, I think, become an interesting and a real technique to be able to apply. So the experiments that we have shows these changes in breakdown pressures. They show changes in fracture complexity for the static fracturing. If we want to use these behaviors in regular hydraulic fractures, then being able to intersect with natural fractures perhaps is an important feature. The lengths of these fractures all scale with viscosity, primarily because the lower this viscosity, the higher the leak off into the formation. So the less volume is there to be able to propagate the fractures. Proppant transport also scales with viscosity. Higher viscosity carries it further, and lower densities also carry it further. And potentially using gelling and foaming agents allow you to be able to increase the effectiveness of being able to drive proppants along the fractures. And so that's kind of the exposition of looking at those things. I will end with a final slide just to make the point that it was Jihao's work, as you see from this, and then the dynamic gas fracturing in the plexiglass samples was Chuangan's work, just to close up. So I will finish there, and with 38 minutes gone, I will be happy to take any questions that might come. Thanks very much.
Yeah, thank you, Derek. As a matter of fact, I mean, Ed Seabrook says it in his first chat comment, what an excellent presentation this was, and covered a lot of material. I don't know whether you can see the chat. You want to go through the chat, or whether you'd like me to transcribe them.
I can get the chat, so you can probably see my screen. There, Derek, excellent question. I agree. Thank you. Dynamic fracturing. I'm interested in the dynamic fracturing example where you determine the limited number of radial fracts. I suspect one can simply determine petal-like branching potential and frequency from the leading edge of a frac in the 3D case. Yeah, so I guess you were talking about kind of self-similar behavior, the kind of things that Leonid Germanovich, as I recall, was interested in looking at a single frac and petals from them. I think it's a similar behavior, is that you can imagine that if you nucleate fractures from that one point around some kind of floor, you could imagine those floors being an infinite number of floors around a surface. They would perhaps be equally disposed to be generating a fracture. And at some stage, the lengths of those fractures start interfering with each other. And, you know, I mentioned the Nemet Nasser paper where you have this, I think is the most elegant way of showing it for a cooled surface, half surface, which has this infinite number of floors. They all develop a small amount, and then after they've developed a certain length, they reduce to by a factor of 2. Every second one shuts off, and then the longer one propagates. Every second one of those then shuts off, and you have this distribution of behavior along there. So I think that's right. So I imagine that you can get this. I think it's the same behavior that you get from the tips of fractures. Yao Huang to everyone. I'm curious about the dynamic fracturing process. Will the favored fracture direction be affected by the combination of in situ stresses, i.e. the ratio of maximum stress over minimum horizontal stress? Yeah, I think that's right. I mean, that was our main point. And I think that's the point of this figure. I think this wasn't Jihao's figure. I think this was a figure by, if I bring it up on my screen, I presume that people can see this, right? Is that right, John?
Yes.
Can people see my screen?
Yes.
So yeah, this is exactly the point from this figure. This is a damage mechanics model of fracturing from a well bore where it's 6-to-1 stress ratio, 6 vertically and 1 horizontally versus 1-to-1. And I think that what's going on in this dynamic fracturing is you completely overcome the stress regime in the near wellbore region, because the dynamic stress wave, by loading uniformly around the 360 degrees of that region, gives a radially symmetric wave. And that's what you see, although it's not shown in perspective here. This pulse wave going from the wellbore into the formation is radially symmetric. If you go out at any azimuth, it'll be exactly the same at any particular time. And so I think that's exactly what's going on. So the fact that you can completely overwhelm the in situ stresses up to some radius away from the borehole means that you can generate fractures which are into the direction of the maximum principal stress, because it's being controlled really by the gas overpressure at the wellbore rather than the in situ stress. So I think that's what I'm trying to say. So I guess if I don't answer your questions, write me another comment if everyone's being very polite and is contacting only by chat. Mark McClure. Hi, Mark. How you doing? Thanks for the presentation. Here's a comment. In recent years, I've become convinced that localized fracture roughness causes localized screen out that improves vertical proppant displacement. I believe it's critical matching realistic data, including that process leads to very different conceptual model for how proppant transports. While a bed still forms, it's no longer a bed, arch, unpropped model. There is an additional region that develops a large proppant trapping region across much of the fracture. Yeah. So I can imagine if I visualize, I guess that's not a question, Mark. I know that. And I know you well enough to realize that's not a question. Yeah, I interpret that as being if you have asperities which close off portions of the fracture, then proppant can get across that. It'll be more likely to be able to be trapped. And if it's trapped, then to not go any further because it gets stopped by the wall and then settles out. And so it gets trapped. Yeah, so yeah, I don't know if I have a comment to counter that. Ed Siebert's also frac turbines to consider in sand transport. Yeah, I'm pretty sure that our models were laminar, and so we did not consider turbine. In the dynamic gas fracturing, do you see any evidence of step-like bursts in frac length generation? No, I think not in PKN. I think you might do in the screen out example. Of course, since I came clean and said that I did not do any of these, I guess I didn't look at very many of the incremental details. If Jihao, if you have a comment to that, I know you were going to be online. I usually have a meeting with Chevron at this exact time on every second Thursday of for project that exactly overprints these meetings. So Jihao, you're online. If you have a question, an answer to that, that'd be great. And thank you. Enjoyed the presentation. So does that mean I should stop prattling on? So I've run out of questions. Sid Green, there's not a question there from you. I can't believe that.
He's at a loss for words, Derek, and I'm really amazed.
Still there though.
Gary, I do have a question. You know, the handoff, when you move from a body wave, the spider type fracture patterns that you've shown so well exist, it moves to a very rapid but not stress wave anymore. And then it gradually slows down to just a rapid and then finally quasi-static and static. That handoff as you go from the body wave to the static, where as you move to the static, clearly the in situ stresses really would dominate as well as other discontinuities. Do you think there's any surprises in that handoff, which is very hard to calculate all the way through? Is there likely to be any surprises in there that we don't understand as you in the real world when you move from the body wave to a static, if you keep the pressure up and just keep extending the fracture?
Yeah, I think it's, you know, I've always thought, I don't know what conventional wisdom is, but I've always, and I know Doug Blankenship always says, the longer you can maintain a high pressure, the better off you are to be able to drive these things. I guess that's kind of common sense in some respects. And so the longer you can sustain this, I guess the better off you are in terms of the gas pressure. This slide is germane because, of course, as you realize in your question, we've sidestepped that. We've done these two separate handoff components. Before using the dynamic wave, and after just using static LEFM to be able to understand exactly what that is. I don't know what's going on there. Certainly Wencheng Zhu's models of these would pick up that behavior, but I haven't looked at that material in detail. You know, this is just a coupling between a flow model and an inertial based solid mechanics model that includes this body force term that allows you to be able to follow that. So I think you can do that. I don't know the answer to that question. I think there might be interesting stuff in there, but I don't quite know. But I certainly agree with you that being able to maintain that overpressure for a long period of time, of course, by having some kind of propellant that continues to discharge or chemically react to be able to sustain that overpressure while you're both propagating the fracture and increasing volume and therefore losing pressure, and also losing it to leak off into the formation, which is also probably quite fast for these low viscosity fluids. So I don't know if I answered your question or not. I'm sure you'll tell
and
me.
And the other area, Derek, you're the world's expert on this probably, is that you've shown very well how the body wave fracture phenomena overpower stress, in situ stress contrasts for sure. For a while. But it's harder to show how discontinuities like a fracture already existing or a layer interface, how does that affect this spider fracture network creation? That's harder to show. Do you think there's any surprises there as to just exactly when will the body wave fracture creation overpower natural fracture interference or layer interface interference?
Well, it's an interesting question. I guess the first wave would be a compressional wave, and it would clamp the fracture, and then the following wave would be tensile in the radial direction, and so it would tend to unclamp fractures and allow them to slip. So I guess it could, for instance, allow kind of shear, hydro-shearing type behavior, you could imagine. I guess the dynamic wave would give you that behavior. The gas pressure wave, I suppose, would behave a bit like how people think of fractures, blunt, propagating hydraulic fractures by allowing the fluid to dissipate along them and being affected by the obliquity of them in terms of allowing fluids to either propagate along them and then jump off them again at some stage, or to propagate the tips of those fractures, or merely not see them if the obliquity is, I guess, high enough to be able to go across them. But yeah, I think they're, as in everything, there's lots of aspects of these we haven't thought about, but be interesting to look at that. And of course, I liked your question, your premise is that you're the world's expert in this. Of course, us professors, we're the world's expert in a vanishingly small area of science. Is what it becomes, I think, just kind of makes it a finite.
No, you're too modest, Derek.
A realist.
Very nice presentation indeed.
So
Okay.
it looks like Sid asked Cheng Ho's question.
Oh yeah, Cheng Ho, sorry. I hopefully answered that.
Anybody else? Just, we got one.
Yeah, okay. So that's where the fluid doesn't go into the formation. Yeah, great.
Okay. Well, hey, Derek, I really want to thank you. It's fantastic. I mean, you saw you had a very strong audience. I mean, more and people are really interested in this topic. And I want to thank you again for taking the time to do it.
Thanks for the invitation. Great talking to you. Great bantering as well before we got going with everybody. So, thanks very much.
Okay, thanks, Derek.
Take care. See you, everybody.
Bye-bye.
Oh, there's Nick Espinoza. See you, John.
Hey, thanks, Derek.